All right.
You know when I'm in a 3-mile.
Let's go ahead and do an example. So, add 1, 2, 3, aka register 3 will have the contents of 1 and 2. NAND 4, 5, 6. Register 6 will have the NAND or the not AND of register 4 and 5. Load word 2, 4, 20. Register 4 has the memory from the contents of register 2 plus 20. Add 2, 5, 5. Register 5 has register 2 plus 5. And then store word 3, 7, 10. The memory from register 3, which should be the base, plus 10 will have the contents of register 7. So we're going to execute this code inside of our pipeline. Yes.
Why are the like the load word and like the save word whatever why is it like the first one and the last one go into the middle one, but all the other ones it's like the first two go into the last one?
That's just the way they designed it.
That's stupid.
Not as stupid as x86.
Good.
You want to go look at that?
No.
Okay. You hold that thought, and I want to just review x86, and then you can come back to me and we'll have a discussion.
I was just thinking though, that is the main advertising point for this. Not as stupid as x86.
It should really be nowhere near as stupid. Like, this is nothing compared to what you have to deal with. All right. Hey, look, it's our pipeline design, but we've I've gone ahead and made a register file and put some numbers in, so it'll make sense. All right.
Whoa.
So what happens in the first instruction? Actually, when this resets, what do all the pipeline registers have?
Nothing.
They had no ops, or as some people like to pronounce them, noops.
Noops.
But it is no op, no operation.
That's what I called it. I called it a noop.
You prefer noops?
Noop.
Again, remember, by convention, register 0 has the value 0.
Noop.
Noop.
It makes me happier to hear noop instead of no.
All right, so what happens first? The add. So, okay, notice we're at time 0. Time 1, we fetch add. That is all we do at clock cycle 1. And then notice we read it from instruction memory, put it in the pipeline register, we store PC plus 1, which is 1. Why is that?
Just start at 0.
Right, all right, we're doing great. All right. Everyone else is nooping, or no-opping.
Noop.
Are there any questions yet? Okay. Notice that the add, which we just fetched, is being decoded, which means they're going to read from register, what is it, 2 and 3? Or I'm sorry, 1, 2, 3. Register 2 and 3, so 2, there's the 9, and, oh, 1, I'm sorry, 1 and 2. I totally lied. So there's the 36, and there's the 9. And that's all it's going to do, that cycle. While that instruction is being decoded, we have decided to fetch the next instruction, which is a NAND, which has the instruction right there, NAND 4, 5, 6. And the PC plus 1 is 2. Why is that?
Because you added one.
All right, we're doing great.
5, 5, 6.
Okay, next instruction. Everyone good so far? Now, notice that the add is an execute. It's going to go ahead and add 36 and 9, which got 45. So 36 plus 9 to the 45. They're not equal. PC plus 1 plus offset's 4. We don't care about that, but we did it anyways because it's a circuit. Stored off a couple other pieces of information. While the add is executing, the NAND is being decoded. It read from what, 4 and 5, so we got 18 and 7. There's 18 and 7, and then stored it off. That's all we needed. And then while those two are executing over there, we fetch the next instruction, which is a load word. There it is in the pipeline register. And PC plus 1's 3, because we just added 1. All right. Anyone confused yet? Okay. So next cycle, cycle 4. The add is in memory, which does nothing because we don't care about data memory in the add, but we do go into the stage because that's the way we designed our processor. It's simply going to forward 45, and then it's going to store that we need to write to 3, and it's an add. While that's being forwarded, the NAND is actually being executed, so the NAND of 18 and 7 is -3. I'm sure you all did that in your head perfectly.
Yeah.
They're not equal. We calculate PC plus 1, but we don't care because it's not a branch, and we forward a couple of pieces of information. Load word, we need to read from, well, we read from 2 and 4, even though we only care about one of them, but that's okay. So there's the 9, there's the 18 from 4. Notice that we have the offset and PC plus 1 and then the load word. And then while those 3 are executing, we fetch the next instruction, which is an add 255. I love how that's actually an 8 right there, but we'll ignore that. And PC plus 1 is now 4. All right, any questions so far? Okay, good. All right, so here's the big one to keep it all straight in your head. Because now we actually have 5 instructions executing, and most of the time this processor will be executing 5 instructions at a time, so this is kind of the picture that you need to see. I always like to read it from the right to left because it makes more sense to me. So the AND is being written back, or I like to say retired, so it's going to forward the 45 all the way back to register 3. It's going to go in the destination as 3. So there's the 45 being updated. That's what the add does. NAND doesn't care about data memory, so it just forwards its information over. We have the load word, which means we need to calculate 9, which was the contents of 4, I believe. And
Yes.
plus 20, yeah. No, the contents of 2, sorry, 2. Plus 20, so you get 29. We calculate whatever, plus offset. We don't care, it's not a branch, but we do it anyways. Store the rest off of load word. While all that's happening, we have an add, and we're reading from what? Registers 2 and 5. So there's the 9, and 5 is 7. So we're good there, and we forward a couple more pieces of information. And then while all that's happening, we read the next store word into the pipeline register 3710, and PC plus 1 is 5. Yes?
So at this point, our CPI is 1? Because we're doing, now we have
Well,
each.
actually, your CPI is 5 because you've gone 5 cycles,
Oh,
but
sorry.
you've only retired 1 instruction.
5, but the next time.
Yeah, you're going to retire another one, so then it'll be 6 over 2, which would be 3.
Yay.
How's it go, Jonah?
Pretty good.
All right, we're only doing 5 instructions, otherwise this will get really long. NAND, writing back the -3 to register 6. Boom. Load word. Hey, look, we're actually going to do something in memory. We read from base, and I think it came up with 99. Sure, that's great. Add. We add the 9 and the 7. We get 16. That's good. And then we're decoding 3 and 7, but we only need, I believe, the 7. Any questions? Load word. We're writing the value 99 to register 4. Boom. Add in data memory. Doesn't do anything. We don't care. Star word. We need to do was it plus offset? So 45 plus 10, 55. Great. Add. We have the 16. Writing to register 5. Boom. There it is. We're storing the value 22 at address 55. All right, we're done. And then finally, we retire store word, which doesn't do anything because it actually did its work in data memory. Any questions? Perfectly good. You got this, Jonah? You ready to write this all in Verilog right now?
So store word.
Well, that's not what I said. I understand the concept. Yes.
So we had already done the data memory when we did the load, right? Or when
Yeah, well, data memory is done during the load and store word.
Right. But now store word already knows that it's been put in there, or will it attempt it anyway?
Well, it did it in this instruction, or this time cycle 8.
Right.
And then over here, it knows not to do anything in write back because it's the store word.
Okay.
But every instruction is going to do each one of these stages.
It's gonna at least go there.
Yep, time graph. So this is just when the add started, cycle 1 completed at 5. NAND started cycle 2, completed at 6. Load word started at 3, completed at 7. Add started at 4, completed at 8. And store word started at 5, completed at 9.
Yeah.
The idea is that if you had thousands of these, there would always be 5 instructions in flight at a time, and you'd be retiring 1 at a time.
Yep.
The reason for that, the reason why that's important is that as you have more and more instructions, your CPI approaches 1. At least hopefully.
Yeah.
But what can possibly go wrong?
Everything.
Good. Name one thing.
Something breaks.
Something breaks. All right, let's pretend the hardware is not the issue, and that the hardware actually
It's
works.
always a hardware problem.
You could try to write to a register file that wasn't there.
What if
Originally
the
you
Yeah, I mean, the instructions can only write to 8 registers, so that's not the issue. Let's see if we can get it. All right. So right here we have a NAND. It's writing to register 6. What if this add had a 6 in it?
You would want what was in 6.
Right, but you didn't have it at that time because it hadn't been written back yet.
Yeah.
Uh-oh. Is that an issue?
Yes.
Yes. Why is someone besides Caitlin, tell me why that's an issue, and me?
Because it wouldn't have the right value.
Right, it wouldn't have the correct value. So that's one problem. What's another problem? It has to do with an instruction branch that we didn't put up here.
Oh yeah, we didn't put it up. What does branch do again?
It changes the PC so you execute the correct next instruction.
Well, if the branch has to go back and like changes the PC, then it's already has like 2 instructions by the time it got there to change it.
Right,
It's
so
already
should we
been
be
executed.
executing those instructions?
No.
No, so we got a branch problems and we got data problems. Did y'all see those two?
So right before we branch, we need to reset.
Well, let's talk about that. It's not straightforward. So data hazards, since register reads can occur in stage 2 and register writes in 5, it's possible to read the wrong value if it has not been written. Oh man. Control hazards, a branch instruction may change the PC, but not until stage 4. What do we fetch before that?
So it's not supposed to be about to be written, it's not been written.
Yeah.
Okay.
And then exceptions, we haven't talked about exceptions, but keep in mind that if you hit something on the keyboard, it has to stop the processor and tell it to do something. And those are called exceptions or interrupts, and we haven't even talked about dealing with those. We probably don't want to right now, so we'll just continue with the first 2. I'm not going to make y'all implement exceptions or interrupt handling. That would just be annoying. Right, David?
We're gonna have a hard enough time with this.
So data hazards. What's a data hazard?
It'd be simple to do their IRQ problem. Just say, put a big message on the screen saying "C system administrator."
Yeah.
All right. So, yeah, we need to figure out what are they, how do you detect them, and how do you deal with them. So, here's the problem. You read from source operand and decode, but you don't write it until stage 5. So here's an example. What if you add 1 and 2 into register 3, but then your NAND right afterwards needs the value of register 3, which you calculated from the add, and the value from 4 to write into 5. So how can we solve this? Do y'all see the problem? Yeah.
Have blank stuff in between.
So we could insert no ops.
Mm-hmm.
Okay.
That would be considered basically delaying it, right?
Yeah, you would be delaying it every time. Yeah. Oh, y'all haven't witnessed one of the funniest solutions in computer architecture and operating systems. You ready for it? You can ignore the problem.
Nice. I like
So we
that
did.
math. Let's go with option A.
Isn't that one that kind of works most of the time, though? No.
It doesn't work here, but it's surprising when it does work. You ignore the problem.
Just make your test cases
Yep.
so that it avoids the problem.
All right, so we have ignore the problem. All right, we'll talk about
Code
first.
around the problem. So don't put those right after.
So here's, whoops, hold on a second. Register 3. All right, let's see if we can detect it. Notice that you have the destination register stored in these pipeline registers, so you can just forward it over here to see if it matches what's coming in. And if it does, then you have a hazard. So you can avoid, oh yeah, that's the other one. You can avoid, make sure there's no hazards in your code, right?
Mm-hmm.
You can detect and stall, and then you can detect and forward, which is what most people actually do, even though it's the most complicated, which is basically fix the problem. So assume the programmer or compiler knows about the processor implementation and make sure no hazards exist. Put no ops in between the dependent cycle. So you do this.
Yeah, like I said.
So you do this in the code. That's what
Yeah.
you're thinking? All right. What's the problem with this?
Just a CPI.
Sure, it increases CPI. Well, actually, no, it doesn't. Your CPI is 1. You're just executing no ops.
Mm-hmm.
Oh. Oh, this is easy. I do nothing. Okay.
Some coders would not know to do that.
All right, so you've been running processors, and all of a sudden you have this new processor that needs no ops. What do you have to do with all your source software?
Change it.
Update.
Yeah, update it. How often do people want to do that? Not. So old programs, legacy code, may not run correctly. Longer pipelines need more no-ops. Programs get larger as no-ops are included, especially a problem for machines that try and execute more than one instruction. Intel Epic did this to the extreme where it would have something called a bundle, which is the compiler saying you can execute these 4 instructions in parallel, and I've already guaranteed there are no hazards. But by doing so, 25 to 40% of instructions are now no-ops. So that's probably a terrible solution. Program execution is slower. Yeah, your CPI is 1, which is great, but some, and by some, way too many, are no-ops. Right, Sydney?
Right.
So detect install. You compare the values, and as long as there's a problem, you just send no-ops down, right, down the pipeline in hardware, and you just keep the current instruction fetch. All right. So how do we do this detection? Well, notice you have these 3 guys, which are your 3 registers that you're going to write to down the pipeline, and you just need to compare it with each of the other registers, which ends up being a lot of comparisons. But you can do that with XORs, by the way, and make sure they're all zeros. All right, keep instruction fetch and decode. So if there's a hazard, you just disable your previous pipeline register and your PC counter. That way it's just going to do the same thing again. And then you pass a no-op. So notice that a no-op was passed. Hazard still detected, so you disable, pass another no-op. So notice that the add is back here, and you have 2 no-ops. And then there's no hazard because we can assume that the register file can read and write in the same time.
Yeah.
All right. What's the benefit of this one?
Gets rid of the hazard.
It inserts the hazard, so do you have to recompile your code?
No.
No, you don't have to recompile your code. So this is a lot better. All right, it's a lot better, but your CPI is going to increase because you're adding instructions. So option, don't stall, fix it. Assume R3 is correct and then fix it later. All right, how do we do this? Well, let's talk about detect install. Yeah, increases every time. Said necessary. Actually, not always. You can reroute the result because you usually just executed it and then forward it back. That's just a funny way of saying it. You're forwarding it back so that it'll have the right value. Please tell me you have another picture of this.
Nope.
No picture? There we are. So here you have an add and a NAND, and there's a hazard. But what happens is the add forwards its value here back to the mux up here, so you got to add another mux, and then it'll use the correct value to the ALU because it detected the hazard. Y'all get it?
Mm-hmm.
No.
No?
I messed up. I lost that.
Let's see. So you read the and you notice that there is a hazard with the NAND coming in.
Right. Okay. So we've detected the hazard.
So you have, notice that the add 1, 2 is going into 3, and it's going to use 3, 4, and go into 5, right?
Okay.
So your add is in decode. Your add, is in execute, and your NAND is in decode.
And our hazard is with register 3.
Register 3. But the ALU result is going to be the value of register 3 that the NAND is going to need. So in your next instruction,
But it's a value of register 3, which is an incorrect value.
So it reads the incorrect value for the NAND, but you've detected the hazard so that you know to move the ALU result up here so you use the correct value. Because you knew that the result from the AND is going to be what the NAND needs.
Well, oh, okay, got you.
Yeah.
But you already have the result in your.
In the other pipeline register, you just need to forward it back to the previous instruction so it gets the correct value.
Huh.
So we fixed that problem.
Yeah.
Nice.
And let me go ahead and go back here. So what hazards do you see here?
Well, now okay, that's writing. What about reading?
Hang on, let's start with this one. What hazards do you see?
Well,
Three at
first
the
one.
beginning.
So yeah, you got the 3 at the 2 at the beginning.
You're adding the same 3 from that used for NAND in the next one.
Yeah. This is also a hazard, by the way.
Yeah.
This one is not, because you can write it
And
back.
write
into,
at the
yeah.
same time.
Yeah, so we're okay there.
The add into 7 is
Store
being
word.
used
Or no, what is
in
that?
the next one. The 7.
Yeah, but you're writing to it, so that's not a problem.
The
Oh,
the
yeah.
load word, it's getting loaded into 6, and then you have the store word there.
There we go. I think it's the last one. For in order pipeline, I believe these are the only issues that you have.
Well, I thought, okay, so we're doing the load word. Was that, what is it, loading 6 or register 6?
It's loading into register
Register
6,
6.
and then it's using register 6 next. All right, we went through this example. Knows that you store the hazards in the pipeline register, so you know what to forward. Right, Sydney? All right, then we're good. Whoops. Oh, the load word. Wait, was there another one I missed? Oh, you must have done the time warp.
Again?
Again?
So there's the load word, register 3, and then we can forward it from there. Okay, great. Here's the problem. And this is what I did not go over. Sorry about that. Are you going to be able to forward the 6 to the store word? Think about your pipeline.
Well, you haven't, you're supposed to, you'll try to do store before you load. Is
The
that how-
store word is stored in
Yeah,
the
remember the
register.
store word's got to do 6 plus offset, so it needs the value of 6.
Yeah.
But load word doesn't happen until data memory, which is
Yeah.
another cycle down the pipeline. So you can't forward this immediately. You do have to stall in this situation. So there is a one stall right here, because once you get the value, then you can forward it. I'll show you that in action
The store word is before.
after I erase the board. All right, so here's the problem. You have load word here, which is going to have a wait, hold on a second. There's a hazard. So you have a hazard with the store word and the load from register 6. But if you think about it, once load word is over here, it doesn't have the value of the word to be loaded because it hasn't gone through data memory. But store word needs to find the offset right here. So it can't do the addition yet. It can't calculate the address.
Yeah.
So you still have to stall for one cycle, pass the no-op, and then now that load word has its address that's loading a word from, it can read from data memory, read the right value, and then it can forward it to the store word for it to use.
Store word is going to use the value out of the x/mem pipeline.
Yeah. Yes.
Those poor muxes have so much going into them.
We have a lot of muxes, don't we?
But Mux is the reason we have it is because it's control. of the
Yes,
data
it's
flow.
really controlled, yeah. Any questions?
Would those be 3x1 muxes? Or 4x1? 'Cause there's
It'd still be a
3.
4 by
'Cause there's a selector.
4 by 1 32-bit.
You use the 4x1 as blocks because you got 2 muxes over there in line to make your.
Well,
you
this
got it, yeah.
this mux is for the first input ALU.
Oh.
This is for the next one. Yep. All right. So how about branches? What's the problem with branch?
like
It's a different path.
it's like
If you calculate the branch here and you realize you need to take it, what about these instructions that are in here?
Add a
they're
load.
wrong.
They are wrong.
They're wrong.
Ugh. So just keep in mind that it's in memory when you send the target to the PC if test is equal, but you already have instructions execute and decode and actually fetch as well, because you're fetching it.
So you want to do the branch before you actually execute anything that could.
Yeah. So yeah, you don't want to do the subtract. All right. So how can we solve this problem?
Ignore it.
We can try and ignore it. What else can we do?
Stall.
Detect the hazard and solve.
Detect install. We could write the compiler so it puts no ops inside the branch after every branch, so this problem doesn't exist. And then we could
Give up.
give up. All right, we'll talk about it.
Save the status. And
So we can avoid it, make sure there's no hazards in the code. We can detect install, and the last one is speculate and branch and squash. Squash. You like squash, don't you? Who doesn't like squash? You don't like pumpkin pie?
Oh, it is a squash, isn't it? I keep forgetting pumpkin is technically squash.
Is it?
Uh,
No.
Yeah, maybe I should tell someone next time to bring pumpkin pie to this one, right? I should have thought, I'll have to note to self. Next student
I'll
write
bring
pumpkin pie.
cookies, but
Pumpkin
okay.
cookies are good too.
So speculate, remember I told you the 3 Ps? There were, what were they?
Pipelining, prediction,
Pumpkin
and
pie.
Parallel. So it's parallelism, pipelining, and prediction. Which one of these is it?
What's that?
Prediction.
Yeah, this one's gonna be prediction.
Yeah.
Alright, so let's talk about the first two first. Avoid.
Yeah.
Don't have any branches in your instructions.
easy.
Yeah.
So no if statements, no for loops,
Yep.
no looping whatsoever. Everyone good?
Yep.
Yes.
Alright, great.
A lot of modularity.
Delay taking a branch. They did this for a while. It was a terrible idea. But delayed branch, instructions of PC plus 1 and plus 2 will execute before deciding whether to fetch from PC plus 1 plus offset.
Okay.
If nothing can be useful be done, then you just put in your nukes or your no-ops. What's the problem? Hey, look, old programs may not run correctly because now you have to recompile your entire pipeline, or all your software. Programs get larger with no-ops are included, especially for machines that try and execute more than one instruction per cycle. If you remember the Intel EPIC I just told you, you often have 25 to 40% instructions. Program execution is slower. Your CPI may equal 1, but a good number of your instructions are no-ops. Does this slide look familiar?
Yes.
Yes.
Good.
Don't do that way.
Don't do that one. Detect install. Wait until you find out if you need to take the branch or not, and then just do it. Alright. At least that's simple, right? So,
Oh gosh.
I don't know about simple.
you just put some no-ops in here, and you just forward the no-ops until you finally have a branch.
Ah.
See? So you're like, oh, I have a branch. And then you go, branch, no-op, no-op, no-op. Alright, what am I doing? Alright, let's execute that instruction. Or fetch that instruction. Alright?
That's a lot of craziness.
It is craziness. So what would happen here? Fetch or fetch. Alright, CPI increases every branch is detected. Is that necessary? One of the beautiful things of branching is you're either going to take it or not. So if you take a guess, what's your accuracy?
50-50.
Right, 50%. So only about half the time the branch is not taken or taken. Let's assume not taken, because then we don't have to try and fix the offset, right? We just say it's not taken, and then if we're wrong, we'll fix it. We ignore so we just ignore it, treat it like a no-op, keep fetching, and if we're wrong, we go back, don't complete any of the instructions, because we haven't done anything in write back. We haven't pushed anything to the register file, so we can just squash the instructions and we're good to go.
Yeah.
Yeah. Do we get a picture of this? I hope so.
Yes.
So we have right here, and maybe you had a subtract and an add. You just turn them into no-ops, and then nothing happens, right? Because you just have to edit the pipeline registers.
Previous 2?
3.
No, you.
Because remember, you're branching right here, so you have an instruction here, and you're actually going to have what's coming from fetch because you don't update the PC until the next cycle.
Oh, so you're gonna run 1 to 1, 2, 3.
Yeah. So you gotta squash 3 things.
And redo it.
CPI increases every time a branch is taken, about half the time. Is it necessary that we are half the time correct? How could we be more correct?
By being
99% correct.
Thank you.
Anyone else?
Solid yes.
Decrease the number of branches. Going to
I know we can't do that.
we can't.
So, you said be 99%. You're on the right track. What's another way of saying that?
Get better.
At
Guessing.
guessing, right. Guess better. Yes, that's literally what we do.
Oh.
No.
All right. Is that necessary? No. But how can you fetch from the target before you even know what the previous instruction branch is, much less whether it was taken? Ah.
Yes.
All right.
Oh gosh.
A separate.
I'm not going to ask y'all to implement this.
Thank God.
That looks very.
You keep a buffer right here
Yeah,
that if you took the branch previously, you store that PC right here as well as what address you jump to right here. Then if your PCs are equal to one another, you use this as the next PC as opposed to PC plus 1 because you last time took that branch. How's that, Jonah?
Good. I like it.
Branch PC, only on a branch if equal. Great. All right, predict not taken. By the way, branch prediction is a huge research topic. You predict not taken, you're about 50% of the time. Predict backwards taken, aka if the address is negative, you're going backwards, you will take that, everything else is not taken. Why is that a little better?
It's more accurate.
Less
Why?
chance.
65%.
Right, we brain a bunch of numbers, end up being 65%, but why intuitively do you think that'd be the case?
Oh, are we talking about predict backwards or whether versus predict forward or something like that?
What this is saying is that if the target is back, in a previous instruction, predict taken, otherwise predict not taken. You write these all the time, guys.
Oops.
Loops, right. Loops usually go backwards, so that's why you have something better. Predict the same as last time. You store a history of what happened last time, and you just do it.
Because generally, in that part of the code, you're doing the same type of.
Yeah, you're usually doing something over and over again, so that's about 80% accurate. Are these significant jumps?
Yes.
Yes.
Yes, this is very significant.
15% each time.
Yep.
Next one will be 95.
Oh, JK.
The Pentium, good try, is 85%. The Pentium Pro is 92%,
Whoa.
using more of a G. Yeah.
Whoa, is that better?
Best paper designs are about 97%.
Paper.
So,
And papers is.
yeah.
Why can't we just be like Pentium Pro?
Well, what?
Because that's you have to pay $5.99 a month after you get Pentium.
I will see you in graduate school and tell you the answer.
Yeah, no.
Graduates, that's cool. That's good.
Yeah.
You really had me hanging on there because I was like, where does this go?
Because yeah, you can get like Pandora Pro or
Yeah,
stuff like that.
Premium.
Spotify Premium.
Just look up G-Share.
You share.
G-Share.
Mine.
What's that?
Come on, then do it right now.
You said we all know you're not doing that.
I'm gonna prove you wrong.